Welcome back, BC Calc students. We're going to take a look at our second video covering example 2 over the convergence of a power series. Our focus here is going to be more so on the radius of convergence. So what is it that all entails? Well, if I take a look here at the graphic and we read the text to the left, think of a power series as a function of x. Laid down the rules there on the last video, how you basically have this summation expression that has this value of x in it, much like we saw our Taylor and Maclaurin polynomials were panning out to be. Now we just say we're going to add an infinite number of those particular terms. So we know that this is happening. We know that we are centered at this value of c for whatever value that might be. And therefore, we are pretty set in that the domain of the function represented would have to be the set of all x for which that power series converges. Because if this power series does some really crazy things, then we don't really have divergence. And I think we're going to be able to show you what these crazy things mean here graphically. So determining that domain is going to be the primary concern of our investigation of the power series. And we really have three different kinds of things that are going to happen. A power series will converge, possibly at a single point. It's not a very good power series if that's the only place where it's reliable, but sometimes it happens. And that place is always going to be at where it's centered. And so that kind of couples with this idea here that a power series will always converge at its center C. And the reason why it does is because if you replace the C with X, then the only thing that you're going to have defined is this constant. And therefore, the function at C is going to equal the power series evaluated at C. They would both be A sub 0, I suppose, in this case. Well, that's not the most interesting power series for sure. One of the more common ones is that you would have convergence on some interval. In other words, if you go out from C and it always would be an equal distance, say in this case capital R in each direction from C, we may have that kind of situation happening. The purpose of this video is to not worry about what's happening at the endpoints. That will come into example 3 in the third and final video. And then finally, the granddaddy of all convergence would be you could have a power series that is convergence over the entire number line. That would be infinity, negative infinity to infinity. There are a few that do that. They're very interesting to study, and we will investigate those as well. So with that being said, how do we determine these types of convergence? And that's going to lead us to our Theorem 1013. This looks very intimidating. There's a lot of stuff going on, but what this basically does is it formalizes those three things that we talked about on the previous slide. A power series centered at C does precisely one of the following things. It may converge only at the center. We've talked about that. Or number 2, there exists a real number r, where r is positive, such that the series converges absolutely for the absolute value of x minus c less than r, and diverges for the absolute value of x minus c greater than r. I know that seems really complicated, but that just explains that second picture from the previous slide that looked something like this. You have convergence on this interval, but beyond you would have divergence. And this really does set up the way that we are going to find that particular convergence. So we'll get into that in some of our examples. And then lastly, the series may converge absolutely for all r, and there probably is a ly that's missing there. Converges absolutely for all values of x. So again, the number r, we're going to use a capital letter to distinguish that, and we're going to call that the radius of convergence. If the series converges only at C, then we don't have a very big radius, right? Makes sense. If you only converge at where you're centered, your radius is nothing. But if you're in case 3, if the series converges for all x, then your radius has a size of infinity. And it's going to be very tricky to keep those two things straight, as you're going to see in a pair of our examples. And finally, the set of all values of x for which the power series converges is going to be called the interval of convergence of the power series. So with that, let's go ahead and take a look at our example 2. It does have 3 different parts to it, an A, B, and here later on we'll see a part C. So question is, find the radius of convergence for each power series. Well, the very first thing that you're going to need to do is pick a test. Pick something that you learned from the very beginning part of Unit A that is somewhat reliable. Think about what convergence test did you use that really took care of some of the more complicated series that you encountered. And hopefully you're all thinking the same thing, and that would be the ratio test. You are going to use the ratio test every single time that you're trying to find the interval or radius of convergence of a power series. It's such a wonderful, conducive test to tackling those kinds of things. So it's likely that you may have forgotten the ratio test, so we'll review that. The limit as n approaches infinity is where you're going to start. And it's paramount that you remember the importance of absolute values. You 100% must use them and continue to use them throughout the problem in order to get the desired answer. So as we remember the ratio test, we would take the nth plus 1 term as our numerator value and then divide that by the nth term in our denominator. And at this point, you would just proceed to simplify this to the best of your ability, and then we'll take a look at the conclusion. So the limit is still waiting out in front, hoping to do its thing. We do our normal simplification that we've seen before. N plus 1 factorial over n factorial is an n plus 1 in the numerator. And x to the n plus 1 divided by x to the n is x to the first in the numerator. Now, things are a little different now since there's a value of x. No longer do you just plug in infinity in for n and say, hey, I've got infinity as an answer and kind of stop. You have to think about what is your desired conclusion for this problem to figure out convergence. Now, I often tell students, if things start to get a little complicated here towards the end, you are welcome to split this apart into 2 separate limit statements by breaking apart at this operation. We're going to be able to do that basically because of the continuity issue with both n plus 1 and x. They can be inferred that we're certainly continuous for both of those, so we can break this apart. Some students don't need to write this step because they can see what's about to happen. In other words, the first limit here is going to be infinity. And then if we multiply that by the limit of the absolute value of x as n approaches infinity, well, we can let n approach infinity all day long for the absolute value of x, and we're not going to get anything other than the absolute value of x. And then in order to converge, let's remember what had to be true about the ratio test. Didn't the outcome of the ratio test, infinity times the absolute value of x in this case, have to be less than 1? So it's really important that we latch on to that particular idea of convergence. And because of the fact that we know that this is definitely not true. In other words, the answer to this is infinity, right? Infinity is the result of our limit. That means that we've lost any possibility to be convergent, except for the one place where we're guaranteed to be convergent. So in this particular case, this particular problem is only convergent at where it's centered. So the answer for the radius of convergence, the capital R, we're going to get 0. And that's where this thing can be a bit tricky. If you get an answer of infinity, that means your radius is 0. We'll take a look at the inverse of that here later on. So we want to be really careful. A lot of students might want to say that the radius is infinity because of this infinity, but it's always going to be indicative of the radius to be 0. All right, let's take a look at part B. The idea to start things off with this summation 3 quantity x minus 2 to the n is very, very similar. You're going to use the ratio test again. And I know that it might seem like a lot of writing, maybe a lot of busy work, but it's so important that you understand if these problems occur on an AP calculus exam, they are typically worth quite a few points. I've seen them worth as many as 4 points. And that would include the step where you're writing the limit statement using correct notation. Of course, properly using the ratio test, and then getting your conclusion. And then as we get to example 3, we'll talk about one last step that might be required. So for this particular problem, I don't think it's going to be too tough to reduce this. You can see that the 3's are going to cancel. You're going to see that x minus 2 to the n plus 1 over x minus 2 to the n will give you x minus 2 to the first. And we can let n approach infinity all day long. And if we do, we would get absolute value of x minus 2. So the limit has basically been performed. It's done its function. And we're just left with the expression absolute value of x minus 2. Now, in order to converge, what must be true? Well, as I said before, the result of your ratio test must be strictly less than 1. Now, in this particular problem, it looks like we have the ability to solve this. It's also possible that if you stop right here, you might be able to tell me what the radius of convergence is, but I want to go ahead and take the extra step or two to solve this. So to solve an inequality with an absolute value that has a less than, we just take the opposite of the 1 in this case, plop it on the left side, make that less than x minus 2, which is in turn less than 1. Basically, we're saying that the value of x minus 2 lies between -1 and 1. And then, of course, if we add 2 to all 3 sides, we would have x is between 1 and 3. Now, we don't care what the actual interval is in this case. Our job is to only determine what is the radius. And so in this case, the radius would be the length or distance that one would travel to get from the halfway point where we're centered, which is at 2, all the way to the far right boundary, which we said is 3. And that would in turn should be the same as to the far left boundary of 1. So in this particular case, the answer to that is 1, which would happen to be the difference between these two values, the positive difference between 2 in this case and 1. And a lot of times that's bothersome to students, and I can certainly understand why. And I always will advise to take that extra moment to go ahead and do this extra step, and then maybe you can see visually a little bit easier from where you're centered how far you have to go out. Besides, most of the problems are going to ask you to find intervals of convergence, as we will see in example 3, and so you're going to be doing it anyway. So here is our result. We therefore can say the radius is 1. Take a look at example C, and then we'll close out the video by maybe looking at some graphical representations of these particular answers to see really what they mean. So for part C, a little bit more going on. We have a much more robust function, or a much more robust power series. So let's start with our good friend, the ratio test. So we take the limit as n approaches infinity of the absolute value. We're going to replace all of our n's with n plus 1's. As you do that, I would certainly advise you to do the simplification. Just do it carefully. If that n becomes an n plus 1, we must distribute the 2 to get 2n plus 2, at which point we can add the stray 1 at the end to get 2n plus 3. The denominator here is going to consist of, again, 2n plus 3, but this time with a factorial. Because we're going to divide by the an expression, I will allow students to go ahead and multiply by the reciprocal immediately. It will save a step, and it would still all be equivalent. And so this is what we're working with right now. As I said before, a lot more going on with this expression. Now it is reducing time. Let's see how we can rewrite this to make it a little bit easier to work with. So first of all, the negative 1 to the n plus 1, I'm going to highlight those pieces here in the orange, and let's see how those might reduce. We see that n plus 1 minus the n is going to be just a positive 1, so we would have negative 1 to the first hanging out on top. Other simplifications that can take place, highlighting the x to the 2n plus 3 over the x to the 2n plus 1. If we subtract the exponents, they do have like bases of x, we would have x to the second power, x squared. And then finally, we notice that we can also reduce these expressions highlighted in blue. You're probably getting pretty good at that. You've reduced factorials many times before. You just have to think here. 2n plus 3 factorial. Well, 2n plus 3 factorial is really just 2n plus 3 times the next integer below him, which is 1 less, 2n plus 2, which is multiplied by the next integer below him, which would be 2n plus 1 factorial, because that pattern continues, and thus we can cancel that 2n plus factorial that was indeed in the numerator. Let's move on to our simplification step. The negative 1, while it resides in absolute values, is going to take on a value of positive 1. If I were to break this apart and isolate in on that, I know this is probably a silly step to write down, nor would I really ever require that a student do this, but you could say the limit of the negative 1 as n approaches infinity, multiply that by the limit of, let's take care of the, doesn't matter which one, absolute value of x squared as n approaches infinity, multiplied by the limit as n approaches infinity of the only thing that's left, which would be the 2n plus 3, 2n plus 2, but note they are in the denominator. That is very important to recognize that. And at this point, you would see that this limit here is nothing more than just 1 times, you can let n approach infinity all day long, and this limit is still the absolute value of x squared. Absolute values have to stick around with that. And then over here, the limit, okay, well, this one's going to be something that we can find. Hopefully you remember that whenever you have a fractional expression where the degree on the bottom is higher than the degree on the top, as n in this case approaches infinity, you would certainly get 0 as your answer. And the absolute value of 0 is just 0. We don't really need the absolute values. And what that's going to do is completely wipe out everything that we have in this expression, because 0 is the result. And remember, what we said is that in order to converge, we need our answer, which, well, before we simplified it, would have been 0 times 1 times absolute value of x squared. We need that to be less than 1. And of course, 0 turned out to be less than 1. So what does that mean our radius is in this case? Well, it means that we're convergent everywhere, and therefore the answer is infinity. And like I said, the biggest mistake that I see students make is to get their infinities and zeros confused. In this case, we have 0 as an answer. Infinity is our radius. If you go back to problem A, we had infinity as the answer to our ratio test, and 0 was our radius of convergence. What I would like to do is quickly show you the 3 graphs that depict each of these series and let you visualize how do you determine or verify these particular convergent findings. So let's take a look at our findings. So if I go back here to part A here in blue, we found that this particular series had a radius of convergence of 0. Well, believe it or not, you can graph, or should I say, try to graph this power series on your TI Inspire or some other robust uh, type of graphing calculator. Desmos would do a fairly good job as well. And if I were to bring up that calculator, I am going to show you what that graph looks like. And just to make sure, this is the graph that we did in part A. I tried to keep the color coding the same as blue. And you're probably thinking, wait a minute, hold on. That's not the series we graphed. That's a series where the upper bound is 10, not infinity. Well, as you can probably imagine, you're going to have some trouble if you try to plug infinity up here. And I would advise you to not do that because your calculator will struggle likely, but you could try to increase this ever so much and maybe use 100. It might take a second or two. But if you do that, I don't know if you noticed, but this graph just got a little skinnier. In other words, this graph really moved upward pretty fast. And that is indicative of telling us that it's really only good for right here along this stretch, which is the y-axis, which happens to be where this thing was centered at c equals 0. And that's why it has a radius of convergence of 0. Now, if we take a look at the second problem that we did here in green, we had a radius of convergence of 1. This is probably the most interesting, at least from my perspective, of the 3. So if I move there and say, okay, there's this graph, and you know what? I don't like its color, so I'm going to change it to green so that it matches our problem. And so there we have it. And again, notice that I've kind of struggled and I stopped at 100. Well, I think on this one, I've got a little bit of leeway that I could play with that, and I could take it from 10 now to 100, and it just gets to be a little sharper, as you can tell. I might want to experiment and maybe see if I could go up to 1,000. It just might take a couple of seconds, yep, for the calculator to think about it, render it. It's trying, and boom, there it is. And as I can see here, it looks as if this graph is not going to be very reliable at all to the left of 1. This thing really jumps up there pretty fast. But between 1 up to 2 and maybe to 3, which means I'm going to have to really pull this down and it's going to have to recalculate, which takes a second or so. And I don't think I can drag this down far enough. But this thing is showing some somewhat reliable behavior for a while. But after we get to this value of 3, then it seems like this is just going to head farther north, farther up, much, much faster. And therefore, we only can rely between 1 and 3. And then finally, our one in red, the one that we just did, we noticed that it had a radius of convergence of everything. So what would this graph look like? Well, there it is. Probably comes as a surprise that that's a straight line. What if I were to take this, say, up to 1,000? It's going to take a second to render. It's trying to find all those points, calculating each of those partial sums and adding them all up until we get to 1,000, and it's going to end up rendering that straight diagonal line once more. Well, because this doesn't have any abrupt turns that take it right up, we can say that, well, at least between -10 and 10, this looks pretty reliable, but I assure you that it would be very well behaved from -infinity to infinity. I don't typically think that these graphical depictions are the best way to verify this result. I think the ratio test is going to be your go-to, but it is nice sometimes to have just a little bit of visual evidence. I hope this has helped a little bit. I know it's a long video, but at least it sets the stage for how to find this convergence. We have another example coming up that's going to add just one little step to this process, and then you're going to be all good to go for topic 1013. Again, we thank you for joining. If you like what you've been seeing, please hit subscribe, and we'll see you next time.